All right, in this lecture, we're moving into convective heat transfer. So we'll begin by looking at the principles of convection. So for a lot of the problems we've been looking at, our external boundary condition, whenever we refer to convective boundary conditions, we assign the convective heat transfer coefficient H, and we have seen this over and over in all of the things we've looked at thus far. But what convection will enable us to do is figure out what the value of H is. And if you recall, way back at the beginning of the course, we talked about what convective heat transfer actually was. And it's essentially transfer of energy between a surface, either being hotter than a fluid going past it or cooler, but it's energy exchange between a solid and a fluid, and that fluid could be a gas or a liquid. So when we're looking at convective heat transfer, what we're going to be considering pretty much for the remainder of the course is going to begin with principles of convection, which is what we will be covering in this lecture. We'll then move into forced convection. And forced convection can be either internal or external. Internal would be an example of the flow within a pipe. External flow would be the flow over a heated fin, for example, where you're forcing the fluid to go over that fin. We'll also be looking at free convection, sometimes also called natural convection. And we'll be looking at convection with phase change. And we refer to this, there are two types that we'll be looking at, boiling and condensation. And finally, we'll be looking at convective heat transfer when we study heat exchangers. So you can see we're going to be looking at convection quite extensively for the remainder of the course. And if you recall, the equation that enables us to quantify the amount of convective heat transfer was Newton's law of cooling. And so through Newton's law of cooling, we have a temperature differential between our free stream velocity and the wall temperature. And the net consequence of that is that temperature differential results in energy exchange or heat transfer either from the wall to the fluid or from the fluid to the wall, dependent upon which is larger. And so we've been using this over and over and over again throughout the course, but one thing that we haven't really addressed is where does H come from? And so that's what we're now going to set out to determine, is how to quantify H. Okay, so in determining H, there are a couple of different ways that we can do this. Now, given that convective heat transfer involves a fluid flowing over the surface, we need to examine that fluid flow in order to be able to quantify the value of H. And consequently, what we're going to be doing, we're going to be looking at analytical solutions. And there are only a limited number that exist. And the reason for that is if the flow is turbulent, we have no analytical solutions for the particular flow field. And otherwise, it's only for fairly restrictive geometries that we can get an analytical velocity profile from which we could then get the temperature profile using the energy equation. And so we'll use analytical solutions. We'll look at a few. But for the most part, what we do in heat transfer, convective heat transfer, is we use empirical data. And so this is data that has been collected via experimentation, and this is quite widely used. And so what you're going to find is we're going to be using different values, mainly the convective heat transfer coefficient, that will be embedded within non-dimensional numbers, and that data has been collected experimentally and then collapsed into these non-dimensional numbers to give it application to geometries that are different from the ones that are studied in an experiment. So they would scale geometrically, but they would be either subscale models or things like that. So anyways, we'll be looking at that as we look at convective heat transfer. So really what that means is that convective heat transfer, within the heart of it, it really is a fluid mechanics problem. And the other thing that we'll find is the convective heat transfer coefficient we'll find that the convective heat transfer coefficient itself will often come from experimental data. And like I said, it will be represented in non-dimensional numbers. For forced convection, quite often we're using the Nusselt number, which is a number that we'll be taking a look at. But that's what we're going to be doing. So we'll be doing a lot of fluid mechanics in this lecture and in the next couple. And then it turns into a matter of collapsing experimental data into forms that we can use for engineering applications. So that will be a lot of what we're doing with convective heat transfer and estimating the convective heat transfer coefficient H.